तो इस लेक्चर में से स्टार्ट करें। तो ये वाला क्वेश्चन देखो, ये वाला तो देखो इसमें क्या है हम लोग को दिया हुआ है कि एस टी हम लोग को दिया हुआ है पावर माइनस अल्फा टी प्लस प्लस में ई की पावर प्लस अल्फा टी प्लस यू टी ई की पावर बीटा टी माइनस यू टी। तो ये पूछ रहा है द कंडीशन अल्फा एंड बीटा फॉर एलटीआर सिस्टम टू रिमेन स्टेबल। अब इसमें क्या है कि देखो एस टी दिया हुआ है, ठीक। तो ये जो है हमारा जो एस टी दिया गया है तो एक्चुअली दिया गया है ई की पावर माइनस, ओके ठीक है। तो रिकॉर्ड हो रहा है, करते हैं। तो हम लोग कह रहे थे दूसरा मेथड, तो मेथड इसने ये लिखा हुआ कि एस टी को लिख लिया, ठीक है। यह ई की पावर बीटा टी यहाँ पे लगाया है समीकरण वाला, तो नहीं होता ये वाला इंटीग्रेशन एस इंफिनिटी मॉडुलस ऑफ एस टी, रनिंग इंटीग्रेशन चैप्टर। ये जब क्या होता है, ये वाली कंडीशन याद है ना, ये वाली कंडीशन फुलफिल होती है ये तो फाइनाइट होता है ना, जो भी एफ की होता है तो ये फाइनाइट। तो हमारा जो फंक्शन एक्स की होता है, तो फंक्शन एक्स की होता है वो होता है टेबल हो जाता है। टेबल क्यों होता है कि ड्यूरेशन फाइनाइट शुड भी फाइनाइट ही रहता है, ठीक है। तो अगर एम्पलीट्यूड फाइनाइट नहीं रहेगा, एम्पलीट्यूड फाइनाइट रहता है, चाहे अगर ड्यूरेशन फाइनाइट ना रहे तो इन्फिनिटी पे t इक्वल टू, अगर मान लो अगर हम लोग का ये फाइनाइट ना रहे तो इंटीग्रेशन पे, तो मान लो इक्वल टू इन्फिनिटी पे अगर हमारा कांस्टेंट है तब भी वो फाइनाइट ही रहेगा, हमारा स्टेबल ही मिलेगा, जो एक्स टी है वो स्टेबल ही मिलेगा। तो ये कंडीशन याद रखो सब लोग कि ये वाली कंडीशन याद रखो, यानी पता ही होगा, मैं बता चुका ये रनिंग इंटीग्रेशन की, ठीक है। तो एक पे कर लेते, ठीक है। तो ही सही। तो अब यहाँ पे देखना होगा कि इन्होंने हम लोग ने ये कंडीशन लगाई और यहाँ पे पहले मैं इसे मिटा, फिर यहाँ पे कंडीशन लगाई, कंडीशन लगा यहाँ, फिर इंटीग्रेशन अलग अलग कर लिया यहाँ से। ओके इंग्लिश वाला, ओके। So as you can see, first of all we have applied this formula, okay. I think you already know, I have already taught the previous lecture. So now after applying this formula we apply the integration on this term, okay, and then we separate the both terms from minus infinity to infinity modulus e power alpha t ut dt plus integration minus infinity to infinity modulus e power beta t u minus t. Now due to this, the ut integration will change from 0 to infinity due to this u minus t, the integration will change from infinity to 0. And now we have put the value of e infinity. So this is the condition that we get. If the alpha is 0, alpha is less than 0, then it is minus, and e minus infinity is 0. And if this is greater than 0, then it is also 0. Okay, so this condition right here is having the range from 0 to infinity. If this alpha is 0, then the graph will be like this. This integration has range from minus infinity to 0. So if this beta is positive, then the graph will be like this. So this is stable graph, stable. So we have proved our method 5 less that is greater than 0, then the function is stable, as we have discussed in the first method. Right here. Moving on. Now see the second question. In this question, we have given h as an into un, dn u minus n minus 1. So an has the range of 0 to infinity, dn has a range of minus infinity to minus 1. Okay, dn is from here, n is from here. So okay, so let us put the value of 0 in an. Okay, so it will be 1 right here. So the value of an is like this. If this is discrete function. Okay, so in the time x domain, we have the graph like this. This alpha less than 0, this theta is greater than 0. So we also want that condition to be satisfied here. So first this in discrete function, we want the graph to be like this. This one, it will decrease like this. Okay, so that at infinity is also the main constant. This from minus infinity, this is 1. So for a power n have the range of 0 to infinity. Okay, so we want modulus of a to be less than 0, so that by increasing the value of n, we get the resultant value less than the previous one. What I am saying is, if modulus of a is less than 0, okay, sorry, not from 1. So now if we put value of a, for example, let me point. So if you put the value of 1, it will give us 0.5. This is by 2. Now if we put by 2 n is equal to 2, it will give us 4. If we put 1 by 2 power 3, it will give us 1 by 6. So this shows us while increasing the value of n, the value of a power n is decreasing, which satisfied our condition to have a graph like this. Okay. Now talking about b. B has a range of minus infinity to 0. So modulus, so this is b power n. So n will always have a negative value. Okay. So we can write this is modulus of 1 upon. This should be less than 1. Okay. Modulus should be less than 1. Okay. So this implies that this modulus b should be greater than 1. We get the value of modulus of a, get the value of modulus a to be less than 1, and we get the value of modulus of b to be greater than 1. So that was the question asking for. Now if we move to second method, we want the second method. This is the second. So in this we apply the formula of running summable, because it is in a discrete value, is infinity to infinity. Modulus of h, it will give us the running so we have write the value of hn like this, and now we separate both by this plus. Now due to this un, the integration will change from 0 to infinity. Due to this u minus and minus 1, the integration will change from minus infinity to minus 1. Put the value of n in a power n, we get the value as 1 modulus a square modulus a cube. So modulus of a should be less than 1 to have a finite value. If the modulus of a is less than 1, then we get a finite value. Now if you put the value of b, minus 1, minus 2, minus 3, so we get 1 upon modulus 1 square, 1 upon b square plus 1 upon b. If this value is finite, when 1 upon modulus b is less than 1. In this, if modulus of a is less than 1, then it is finite, and in this, if 1 upon modulus b is less than 1, then it is finite. This implies modulus should be greater than 1. So we have found that if this value of a is not less than 1, for example, let's say it is greater than 1, it is 2. Okay. So 1 plus 2 plus 2 square plus 2 cube up to infinity, so we get an infinite value. So it is not desirable. Get an infinite value, it is not desirable. This 1 upon modulus of 1 upon b. So let it say modulus of 1 upon b is greater than 1, and modulus of 1 upon b is 4. So if you put the value of 4 here, 4 plus 4 cube plus 4 square plus 4 cube, so it will give us the value of infinity. So we do not want the value of infinity, because the value infinity is uncertain and it is not desirable. So to have a finite value, this modulus of a and this 1 upon modulus of b should be less than 1. So yes, so less than 1, then we get the simple b greater than. So now the second question, this one, this is third question. It is given as u n plus 3 plus u n 2 plus 2 u n minus 7. So if take an observation on the coefficient of each term of sum of the coefficient is not zero. Okay? So the duration is also infinite, okay? And they have a finite amplitude. You can see they have a finite amplitude. So it is a power signal. System is a power signal. So it is not a causal signal. It is unstable LTI system. And it is a non-causal LTI system. Okay. So now, if we draw the graph of this thing, so it will like this. Please select. If we draw the graph, starting from 1, and it will goes to 2, 2. Okay, this is up to 7. Plus 1, and then it will get a plus 1. Get this is 1. At sorry for my 2, 7, 7. Still like this. This is the, for example, let's say it is H. So the will be like that will increase, amplitude will be increased by 1. So this is 2 and this is 1. So kept is 7. So it is not this action is causal. Okay. It so actually let me check if it is recorded. Yes, it is. See, this is not a finite amplitude. See, let's say it is. Let's say it is st. It is an time domain. Okay. So if you want the graph of this, it is from -3 starting from 2. It will get a first step up of +1. So at 2 it will get a step up of +1. It is 2 and this is 1. So up to 7 till 7 the amplitude is 2, and at 7 it will get a upward step. So this action here is not, it is having an infinite duration, okay, and its amplitude is finite. So it is a power signal, okay. Amplitude is finite, so it is a power signal. Its amplitude is infinite, sorry, its amplitude is finite and its duration is infinite, okay. And it is not a causal signal because it is starting from n less than 0. So this action is having infinite duration. So, and also if we find the value sigma n with infinity plus of hk, then it will not be finite. If not be finite, so this implies it is a power signal. It is a power signal. Why it is non-causal? Because this is starting from n is less than equal to 6. Now moving to this question, you see this is a function, this is a sinusoidal, this is a function. So we write 1/2 power n un as a single function. This is now multiplied by a sinusoidal. So first we draw the graph of 1/2 power n un. Okay. So now if we draw the graph of 1/2 un, so this have a range of 0 to 30. So while increasing the value of n, if we increase the value of n, then the overall value will be decreased. Okay. So if it is starting from here, sorry for the sound. If it is starting from here, the graph will be like this. And now we take the mirror image. Now in between, we draw the sinusoidal curve finally. So as it is to draw plotted curve, a discrete function, so we draw the graph like this. So as you can see, this is causal because it's starting from at n greater than 0, and also okay. So we are here now static and dynamic LTI system. So remember this note, okay, that if an LTI system to be static, the unit impulse response, that is for an LTI system to be static, unit impulse response STHN must be impulse response. So if ST and HN is impulse response, then we can say that the LTI system is static. Focus on this. If you want to check the system is invertible or not, then its unit impulse response is HT in time domain, in discrete time domain, in continuous time domain, HN in discrete time domain. So convolution with this inverse, if for inverse, if us impulse function, we take the Laplace transform this, and this convolution is converted to multiplication, so we put dot this s, this Laplace of LT is 1. From here we get that this inverse is 1 by h, and in discrete is like n. Now in this discrete time domain, we take z transform will be h z into h z into 1. We get h z. Okay. Now unit step response of an LTI system. So if you see, when we pass a function ut from an LTI system, then convolution of the system will take place with the function in the LTI box, in the black box. Okay. So as you can see, del t is h convolution. As you know that if you take any convolution with the ut, the integration of that function will take place, running integration. So now this del t is equal to integration 1 infinity to t h tau deta, or you can say that this ht is t del t upon dt. So we have to remember this t del t upon dt. So in any question, function is given like an input is given. If the input is being passed through an LTI system, output is given. They are asking about what is the unit impulse response ST or HM. You can find it to sort it. No, only ST. First find ST, then del N. Step 1, take T is d by ds of del t, as you see here. Okay, now simply take the convolution. Take yt ht. Now in discrete also, this we can, all the steps are similar to the above. In this we have to remember only this part, right? Del n, if del n minus 1 is this one. So as we have now learned both of these terms, this is in field. Now in this question, the response of the LTI system for an input 2 ut is minus t ut. So the input is given 2 ut. So this 2 term will also come in the output to be write 2 here, 2 del t. Now we put the value of del t, that is this. Now we get a del t as by 2 to the power minus t ut. Then we perform ht is d by dt of del t. This is performed here. You can see performing a step, we get our get the required unit impulse response answer. Now see this second question. In this second question, we are talking about the discrete function. So the system unit impulse response is given as, we have given the output del n, and the question is asking find the input of the system. It is discrete, so we know in discrete that h is del n del n minus. Del n is given as 1, 2 and 1. So we add a 0 because it will help us. Now del n minus 1 will be, we shift the arrow. This is the graph will shift right, the arrow will shift left. So we shift the arrow from 2 to 1, 1. 0, 1, 2, 1. So now if you put the value of del n and del n minus 1 in this equation, then we get the values of hn. Okay, so at n is equal to minus 1, this is 1, this is 0, so this will be 1, this is 0, 1, and at n is equal to 0, this is 1, this is del 1, this is 1 minus 1, 0, del 1 and 0, so again 1, n is equal to 1, this n is equal to 1, it is 1 and 1 minus 2, so it is minus 1, and at n is equal to 2 is 0, 1, so 0 minus 1 is again minus 1. So we get this hn, and the value of xn is already given. So we want the new, we want yn to y, because this right here is the unit step response. This is the unit step this yn is So we solve this by tabular method. Add the values of in here, in here, and divide this table, and then we get our resultant IN output. So the table, the summary of that all that we have done for causal, for stable, for static, and for invertible. So for a continuous LTI system, this HT should be 0. At is less than 0, then it is a causal system. Okay, and in discrete also, Hn is 0 or n less than 0 means n is less than or equal to 1. For stable, this condition, that is infinity, minus infinity to infinity, modulus of h tau comes out to be finite. For static, if ht is in the form of a del t or a del n, then it is static. And for invertibility, this, if we take convolution of st with this inverse, then it will give us impulse response, then it is invertible. Okay, so now we are starting Fourier. After this chapter, we are going to study Fourier transform. Okay, so now what is the basic definition of Fourier series? It is that if the Fourier series is the representation of time domain non-sinusoidal periodic signals as a weighted sum of harmonically related mutually orthogonal signals. Basically, we use Fourier series to write the non-sinusoidal signals in the forms of periodic and sinusoidal. For example, this is a periodic and sinusoidal curve, sin t. But if we want to write, we can write it like a omega t. We can write like this. But what if we want to write the graph of this one? This graph cannot write because it is not sinusoidal. Not sinusoidal. But it is a graph. So how can we solve if someone gives us to write the expression of this graph? So to solve and to write these graphs in the form of sinusoidal periodic terms, Fourier series is come into picture. So if we want to write these terms in the form of sinusoidal periodic signal, okay, we can write this graph in the form of, if we break in three terms. First is this constant, then these two terms. These two are sinusoidal. So we write this non-sinusoidal plus periodic function. Okay, so it states that Fourier series provides a method to break the time domain sinusoidal periodic signals as a weighted sum of mutually orthogonal harmonically related sinusoids. So what is the purpose of the Fourier series? The purpose of Fourier series is to calculate the frequency of time domain of non-sinusoidal periodic signals. Frequency of time domain signals cannot be calculated just by looking at time domain signal, except the time domain signal is a DC or sinusoidal. So you cannot find time domain, okay, because it is in time domain and we cannot find the frequency. Can't comment as xt is in time domain, and this is DC, so we can say that it has 0 hertz. This is sinusoidal. If you take frequency, it is omega rad per second. So there are three types of Fourier series: trigonometric Fourier series, polar form of Fourier series, polar form of trigonometric Fourier series, and the complex one. So this is the formula. This is the of trigonometric Fourier series. This A is a constant, okay? And this an is bn. This a naught, an, bn are trigonometric constants. You do remember this expression because it is very useful. Questions are directly come from this formula. So repeat with me: xt is equal to a naught plus sigma n is equal to infinity to n is equal to 1 to infinity an cos n omega t plus bn sin n omega t. Remember that with an this cos n come, and with this bn this sin n omega t, omega naught t will come in picture. So this is a non-sinusoidal curve. Okay. T by 2, this is t naught, this is 1 pulse, this time period is 2 by omega naught. We want to write this in the terms of sinusoids, because it is not sinusoidal, you can see. But if you want to write in the terms of sinusoid, then we can use Fourier series. So we write a naught sigma n is equal to infinity to n is equal to 1 to infinity an cos n omega naught t plus omega naught t. And now we found out that t naught is 2 by 2 pi by omega naught. Okay. So now we expand it. Okay. an cos omega t, a2 cos 2 omega t, so on with tn. This we also get that this t1 is 2 pi by omega naught, this t2 is also 2 pi by 2 omega naught, and t1 dash is 2 pi by omega naught. Okay, so what is the formula of an? What is the formula of an? So it is, let me write with me, is an a naught integration of one time period xt dt divided by the whole time period. Okay, it is also area of xt in t naught, yeah, xt in divided by the T naught. This is the area of xt from here to here divided by T naught. It will give us the DC value or the average value or the mean value of xt. It is all the same name of A naught. A naught is DC value, also called as the average value, also called as mean value of xt. So if you want to find A naught, take integration from 0 to time period, from this time period T naught, and divided by the whole time period. And if the formula of An is 2 by T naught integration this function, time domain is T naught, okay, and same with this also, here also. Now remember, in both formula of Bn and An, both have 2 by T naught outside the integration, okay? And this A naught only have 1 by T naught. If you see this way, 1 by T naught outside. Now we take the integration with the limits of time period at xt cos n omega naught t dt. Okay, and now with Bn, we know with Bn sine comes into picture, as you can see here. With Bn this is sine, and with An it is cos. We write 2 by T naught integration T naught xt sine n omega naught t dt. In this both condition, n should be greater than or equal to 1. This is the table. Xt is real, and it is when A naught is real, An is real, and Bn is real. If xt is real, then every coefficient of the trigonometry is real, and if xt is purely imaginary, then every coefficient of trigonometry is imaginary, purely imaginary, and if it is complex, then all of the are complex. So as you know, I have right here An formula is, write with me, 2 by T naught. Take the integration of limits with time period, write the function xt, and with An what comes into picture? Oh, it is cos n omega naught t dt. Condition is that is greater than or equal to 1. So replace this n with minus n. This see what happens. What is the formula of A minus n? This is the formula of A minus n. If you replace n here with minus n, then also this whole term will be remain same, because we know that cos minus n x. So find this. Remember that An is equal to now Bn. If we write with me, Bn is equal to 2. It is Bn of 2 by T naught. Now integration over this time period is T naught. Now we write the function. With Bn, what comes into picture? It is sine n naught t dt. Condition is n is greater than or equal. If you want to find that what is the formula of b minus n, so replace this b replace this n with the minus n, as we all know that sine minus x is x. We will get this relation. Pn is equal to minus times b minus n. Kn is equal to a. Remember the formula. Remember the formula. These two. Remember these conditions. These two conditions. Now moving to the polar form of the trigonometric Fourier series. This is only valid for real-time periodic signal. If xt is real, we all know that an, a0, an, bn all are real. Also remember this table. Okay. This is the polar form of trigonometric Fourier series, and in this xt is real time domain non-sinusoidal periodic signal. You all know the general formula of this Fourier series. So right, do this. This xt is the general formula a naught sigma equal to infinity 0 an, and with an cos will come, so cos n omega naught t plus bn, and with bn sine will come, sine n omega t. Now in this polar form, the value of an is here r cos phi n. The value of bn is r n. What is rn or what is? So rn is the mod of an and bn. It is under root an square plus bn square, or is simply is phi n. It is tan phi or tan inverse bn by an. Here this n is greater than or equal to 1. Phi naught simply 0. N is equal to 0. So this is the polar form. This is the polar form of trigonometric series that we will learn. Remembered. So write with me. Take your pen and write with me. Right here. The polar form of trigonometric series. What is that? This shows xt in a. At the place of a naught, it is r naught. With r naught, the sinusoidal terms will come into picture. So take sigma n is equal to 1 to infinity. The limits will remain same. Right? Cos n omega naught phi. So where this come from? See here. this, we write n is equal to infinity, n is equal to 1 to infinity. Now we write Rn cos phi n. At the place of an, we put the value of n. So R cos phi n is cos n phi, cos n omega naught, cos phi n cos omega naught. Thus, at the place of Bn, we put the value of this R n sin phi n sin m t. So we take the Rn common. Okay, take this Rn common. Now see, this is the formula. Okay, cos p is a p. This is cos a, this is cos sin b, a minus, and we have to remember this term, last expression. Now again write this. Write with me. The value of an here is Rn, not R naught, Rn, and with an cos will come cos phi n. The value of Bn is Rn sin phi n. And value of Rn will be square both of this term and sum and addition and add them, square them and add them. So we get Rn as an square plus bn square. So this term we have to remember also that R naught is equal to n naught. Okay, what n naught is a naught. Now if you remember, we have studied earlier, this is the graph of a non-sinusoidal, non-periodic, non-sinusoidal, and we write this in the form of periodic terms. This is a naught, which is a DC term, and the rest are the sinusoidal term. So same with our polar form, this one. If we expand it, so if we expand this term, okay, so we get xt is equal to this R naught from here directly, and now put the value of n in this equation. We get Rn cos omega t minus phi n, R2 cos 2 omega t minus phi 2 n, and this n, and so on. So R naught is the DC component of time domain on sinusoidal periodic signal of xt. So the frequency of this, we know that frequency of a DC component or a constant is 0. So what they are telling here is, let me show you. For example, there is a graph. This is actually okay. So this is the graph. So now they are asking for the amplitude. So we know the amplitude is By looking at the graph, the amplitude is A. What is the power? So study that the power of a full DC is take the modulus of the amplitude and then square it, and the RMS value under root of power. So simply get. Okay. So in this term, we are using R0, we are using A. Okay. This good. Okay, now in these two expressions, this expression and this is the resultant. So let me explain you this one and you will get to know the rest. For example, amplitude is with this. Have you remembered that here it is. Want to find, this is a sinusoidal term. You all know that the sinusoidal term. So what is the power of this term? This value is the power of this term. So we all know that the power of this sinusoidal term is that we take the amplitude, then mod of this amplitude and square it and then divide it by 2. We have already studied that the power of sinusoidal is amplitude modulus of the amplitude square divided by 2, and we know that find the this under root power. If we take the under root of power, then you get a the same reduce. Now these are sinusoids. This is their root. So the power is, you can see here, the amplitude square divided, and the RMS value is the under root of this. We take under, and we know that we have studied earlier that what is the value of R1, then it will be under root 7 square. Simple. So I hope you understand. Yes. So see this one. This is the expression of this function. It is like R0 square plus R1 square by 2, R2 square by 2, R3 square by 2, and so on. This comes after this. Now see this term, this graph. We all know that if we want, we can write this in terms of these quantities. We are writing in the style of polar trigonometric Fourier transform, Fourier series. We write R0 r1 cos omega t minus phi 1. Okay, now r2 cos 2 omega t minus phi 2, so on. So what is the power of this constant term? It is simply square of that term. What is the power of this sinusoidal? It is root square divided by 2. All these terms to infinity are sinusoids. So r1 square by 2, r2 square by 2, r3 square by 2, and we know that uh, plus 3 can be shown this power of sinusoidal of a square. So okay, this graph tells us that the power of this graph is xt, is px modulus a square by tell us that its power is a, and by the conventional method we also find we break this graph, write it in the terms of these small sinusoids and a constant term, and then we take the power of this, and then we equate these two equations, and that is simply called Parseval theorem. It's nothing something special, but it is just simply equating two equations, power equation, by two different methods. So moving forward, this is frequency domain analysis of time domain non-sinusoidal periodic signal. Okay, so all the thickness one. See this question. We have given Rn is equal to sine An and Bn, and if you want to find the absent harmonics in this, so how can we find the absent harmonics in a form of polar form of Fourier series? So Rn is given sine An Bn, and A is given as pi by 2, B is given as. So the first step is write this in the form of sinc function, as we have all know sinc function. So how to write in form in sinc function? So first of all, forget about this sign. Think there is no sign, so only An upon Bn will be remain. So write An upon Bn. Now the term with sign, it is An, so write thing at the place of sign thing, and then divide the term which is the coefficient of, and divide the term inside sign by a pi, so it is An by pi. So we write this sign An by Bn in the form of sinc. Now we want to make this 0 because we want to find the absent harmonics. So as we know that a sinc function is 0 when the term inside this is equal to 0, is equal to a constant like An, same An by pi is equal to k. Now this n will equal to n pi k pi by a, and we have given that is pi by 2. So k pi 2 comes, but we get n in the form of 2k. So if we put different values of n, different values of k, like 0, 2, 3, we get the accent harmonics. So if you put 0, it is 0. So if you put 1, then it will give ns 2. If you put 2, if you put 3, put 2, it will give us 4. Put 3, it will give us 6 and 8. So the accent harmonics is second, 6 and so on. Also, there is no DC, so also the DC is absent. So this is the step. First, what we have to do, write this given sine a by b in the form of sinc, and equate this sinc equal to 0. Now we know a sinc will be 0 if inner term will be equal to a integer k, and from there we find the relationship between n and k, which is n is equal to 2k. Now we put the different values of k, find the different values of n, where the Fourier series is absent. Harmonics are absent in the Fourier series. Now we are moving to the next type of Fourier series, that is the complex exponential. So as we have already know that this is a non-sinusoidal periodic signal, and we can write this in the form of trigonometric Fourier series, that an plus sigma n is equal to 1 to infinity an cos n omega naught t plus b n sin n omega naught t, where this constant has these value. A naught is time period of the first term, time period of the first curve divided by the whole time period, is 2t. In am and bn, 2t will come into picture, and we take integration of the periodic, and with an there is cos, and with bn there is sine. So the expression that we remember is gonna be this one: xt is equal to this is the term xt. These are the constant. Now write with me, because I always write. So here we are. Complex. We can say it complex, or we can say it exponential. Exponential Fourier series. What is the formula that we should remember for this complex or this exponential Fourier series? First, write this, and from now infinity to infinity, this is constant, and e power A omega naught remember this Jn this e power Jn omega naught t is the what is this Cn. C0 and Cn are the coefficient of exponential. So we have to remember these two terms, these two formula. The value of constant C0 is integration of one time period divided by the time period, just like A. For C 20 take integration now C, it is exponential, so minus j omega naught t dt. So know all these are of trigonometric Fourier series. Trigonometric Fourier series constant an bn. We are finding a relationship between these two Cn and an bn. So we are finding here the relationship between the Fourier coefficient of exponential form to the Fourier coefficient of trigonometric form. So the Fourier coefficient of exponential forms are C0 and Cn, and the Fourier coefficient of trigonometric Fourier series are A0, An, and Bn. So we are switching directly to the result, and I am skipping the derivation because it's not important for us to remember the derivation. Okay. So the result is here. Is here. Cn is equal to An by 2 minus j Bn by 2 and C0 is equal to A0. Now if you replace this n with minus n, then A minus n will, yes, A minus n by 2 minus j B minus n by 2. Now we find that this C minus n is An by 2 minus j B by 2. We have found earlier that A minus n equal to An, this B minus n equal to minus. Now we put the value of both of these A minus n and B minus n in this term. We find that Cn minus C minus n square n by 2 plus n by 2. We write the formula of Cn is by 2 n by 2. So from here get that Cn equal to C minus n. Cn equal to C minus n conjugate. So this both of these terms, this C minus n is important, Cn is important, this is also important. Now you see here that we have to this Cn is An by 2 minus j Bn by 2. This C minus n is An by 2 plus j Bn by 2. So if we take the modulus of this n, then we get root an square plus bn square by 2 and root an square plus j and root an square bn square by 2 is Rn. Okay? And if you want to find the angle, then it is simply tan inverse Bn by A. Okay. So now if you want to find the angle of Cn, simply tan inverse Bn upon An. Simple. We get that. Moving forward, what we have to know, the modulus of Cn phase Cn is phase spectrum. This is magnitude spectrum, yeah, phase spectrum. This is a summary that we all have to look at. So first is that Cn is equal to C minus n conjugate. Cn is equal to, write with me. I want to write. Can we write? Okay, now, so let's write together with me. First one. First one is that this Cn is the conjugate and Cn equal to n by 2 Bn by 2 C equal to n by 2 plus j Bn by 2. Third is what is the modulus of Cn? Modulus of Cn is Rn by 2, where this R is greater than or equal to 1. And what is the angle of Cn? Angle of Cn is tan inverse Bn by n, where this n greater than or equal to 1. Fourth one is modulus of C minus n. It is also Rn by 2 same is greater than or equal to 1. The change is in the angle, which is we called phase. It is now plus. It is not minus. It is plus tan inverse Bn by 2. Sorry, not Bn by 2. Bn by An, where An is greater than or equal to 1. Or write the fifth one. Fourth one. Modulus of plus of m equal to plus of p sin. Magnitude spectrum is even. We call this even. The angle section in CM, which we call phase, is equal to the minus of minus. We call phase spectrum. QT, ठीक, ये दिया गया, ठीक। और ये वाला तो दिख ही रहा होगा, उन्होंने इसका बना लिया ग्राफ, दिख रहा होगा यहाँ। तो अभी यहाँ पे दिख रहा होगा, तो नहीं रहेगा। तो देखो होगा क्या है, हम लोग ने सबसे पहले देखो यहाँ पे क्या हुआ है, हमने क्या किया, जो क्या हुआ एक्चुअली दिया गया था ऐसा, की पावर माइनस अल्फा टू ग्राफ कुछ ऐसा होता, इसका इतना पार्ट ले लिया और बीटा टी का ग्राफ है, इसका इतना ले लिया, ये हम लोगों को बनाओ। अब यहाँ से अगर हम जो अल्फा है तो लेस देन 0 होगा, तो और जो बीटा है वो ग्रेटर देन 0 होगा, तभी स्टेबल होगा। ये तो मेथड 1 हो गया, ठीक है। तो दूसरा आता है